started in a second. Okay, so let's just recall the notation here once again. A game's outcome is labeled N if the current player, the player who has the turn starting at that game, has a winning strategy from that position. And it's a P-type otherwise. So if the current player doesn't have a winning strategy, then the other player does. And in particular, we are looking here at games that don't have draws, and that's why one of these players must have a winning strategy. I did not explicitly show that one of the players always wins, but from the discussions we've had about the game tree, hopefully it's apparent how this works recursively, right? So that's what I wanted to say about recapping the notation. Let's just do a couple of quick facts to warm up. So this is one of the things we saw yesterday, that if G is a game, this can be any impartial game, then G plus G is P. And this is essentially by mimicking. Okay, I never know the spelling of mimicking, so let's just assume that that's correct for now. But yes, so to tell you that the game is P, I have to give you a winning strategy for the opponent. And the strategy for the opponent is simply to say, I'll wait for the current player to make their move, and whatever game they pick and whatever move they make, I'm going to pick the other one and make the same move in it. So in some sense, you maintain this invariant that once both players have made their moves, the game always looks like G plus G for some game G. And because we are looking at games that have finite play, at some point you're going to get to a game where the current player has to get stuck in one of the games, makes the last move in one of the games. And when the other player mimics that move is when the entire game gets stuck. So the other player has the last move. So hopefully that's reasonable. And this is something that we'll just keep invoking as a fact every so often, so it's useful to remember. Now, a follow-up to this is that if you look at the game that is the sum of two singleton nim heaps, which I'm going to start to denote by star n because that's the standard terminology around these things. So I'm looking at the sum of two singleton nim heaps, which is basically the standard game of nim with two heaps of sizes n and m. And I want to say that this is P if and only if n equals m. So one direction follows from what we have already seen. So if n equals m, then the game is P. This follows from the previous fact. And what about this implication? We want to say that if n plus m is P, then it must be the case that n equals m. Now, suppose not, right? So we're going to show this by contradiction, if you like. So let me just write down what we want to prove here. If and what we do for the sake of contradiction is, well, suppose not, right? So suppose n plus m is p. Suppose this is true, but n is not equal to m, right? So we have that n plus m is p, even though n is not equal to m. But if n is not equal to m, then without loss of generality, let's say that n is bigger than m, right? And the current player can therefore remove n minus m tokens from the n heap, the bigger one, and basically transform n plus m to m plus m. And this we already know is p. From the previous fact. And in general, if you have any state that has a p child, then that's n, right? Because that means that you have a strategy by just pursuing the p child. So this is just useful to have in your bloodstream from any state S. If you have a p child, then that state is a n. And conversely, if all the children are n, is when the state is a p. Right? So in this situation, we are able to discover a p child, which means that the current state is in fact a n. You don't have to actually phrase it as a proof by contradiction like I just did. It's really a simple direct proof. If n and m are different, then there is a p child. If n and m are the same, then the other player has a strategy by mimicking. So that's really all that there is to it. And so this is still in recap territory, but these are bits and pieces that will be useful. So that's the second thing that I wanted to point out. And the third thing that we claimed yesterday without proof, but let me just try to argue it a little bit now, is that if we have a game A, which is P, then the outcome class of G and G plus A are the same for any game G. So what we said yesterday was that the P state has the so-called zero behavior, which is that if you add a P state to an N state, you get an N. And if you add a P state to itself, then you get a P. And we want to argue both of these aspects. So in particular, let's say that G is a P-type of game, which means we want to show that P plus P is P, right? And the winning strategy of the second player here, because this is what we want to show, that the second player wins the overall game, right, is that they keep pursuing their winning strategy separately in both of the individual games, right? So no matter where the first or the current player moves, they're moving in games where the other player has a winning strategy. So in some sense, the winning strategy for the combined game is simply the union of the winning strategies for the individual games. Okay, so the and notice why this does not work if you are working with an n plus n game. From n plus n game, the current player has a winning strategy in both the games, right? But for example, they can immediately win one of these games and finish it off, right? And now they're left with an empty game with an end game, and this is the state that they offer to the other player. And now the other player has a win starting from here, right? So that's where you get stuck if you were starting with an n plus n, because you can morph the status of one game and you could give an advantage to the other player in the other game, right? Whereas in a P plus P situation, the other player waits for the current player to make their move, and they make their best move in whatever game was touched by the current player to begin with. So I think it's worth spending some offline time appreciating sort of the slightly nuanced differences here between the P plus P and the N plus N situation. But now let's say that the outcome class of G is N. And now what do we want to say? We want to say that a N plus P is a N, which means that we want to find a P child, right? So here, as a first player, I know that I have a move in G, which is going to transform G to another game H. And I know that H is going to be a P child. That's the meaning of G being N, but I have a P child. So now what happens if I make this move in the meta game, in the combined game? I take G plus A, and this is a move that's available to me. I'm going to pick G. Sorry, I think I have Stage Manager or some such funny thing activated, and I haven't figured out how to deactivate it yet. So you'll occasionally see my being confused with what's happening on the screen. But anyway, so coming back to the proof, the first player picks G and makes the move that transforms G to H. So this is the new game. And in the new game, notice that both the component games are P, H is P by choice, and A is P by assumption. So this game is a P plus P, but we've already established that P plus P games are P. So we know that the meta game has a P child and therefore must itself be a N. Okay, so I hope that these things are making sense so far. And just to recall the definition of equivalence, we said that G and H are equivalent if for all third-party games J, the outcome of G plus J is the same as the outcome of H plus J. So notice that if two games are equivalent, they must themselves have the same outcome class, because J could be a P game, for instance, in which case, if J is P, then this would be just the outcome of G, and this would be the outcome of H, and they have to be the same. So that's sort of a prerequisite for two games to be the same equivalence class. You cannot be equivalent if you don't have the same outcomes yourself. So a P game is never equivalent to an N game. But it turns out that this equivalence relation is much finer than just saying dump all the P games in one bucket and dump all the N games in a different one. There's a deeper classification because, to begin with, for instance, we've said that N and M are equivalent if and only if N is equal to M. So each NIM game with a single heap with whatever number is a different game on its own right. It's a different equivalence class on its own right. Okay, so, and once again, hopefully, the reason that they are different equivalence classes as per this definition is clear, because if you have N and M being different, and let's say that N is the larger number, then we bring in M to both games. So in some sense, this is my choice of J. And notice that these equivalence classes are not the same. This one here is a P, and this one here is a N, as we saw earlier. What we said earlier was that N plus M is P if and only if N is equal to M. So that's what I'm using here. Right. So indeed, N and M fall into different equivalence classes. And here's a cute sort of a shortcut for determining if two games are equivalent or not. So turns out that G is equivalent to H if and only if G plus H, this meta game, has type P. So this is sort of our next claim. And again, one of these directions is easy in the sense that if G and H are equivalent, so let me break this down into two parts. So let's say first, we try to show that if G and H are equivalent, then G plus H is P. But we've seen that when G plus H are equivalent, then G and H have the same type. So in particular, want to say that if G is equivalent to H, then actually, I'm not sure if the fact that they're the same type is as useful as being able to say the following. So here I'm just writing down the definition of what it means for two games to be equivalent. You can bring in your favorite third game and add it to both, and they will have the same outcomes, right? So what's a useful third game to bring in? A useful third game to bring in is one of G or H. So I'm going to bring in, let's say, G. And why is this useful? Because we already know that G plus G is P. This was by mimicking. And because that's now equal to H plus G, we know that H plus G must also be P. And that's what we wanted to show, right? That's at least the forward implication, which is that if G and H are equivalent, then the sum is P. Now, on the other hand, we want to say that if the sum is P, then G and H must be equivalent, right? So what do we want to show to say that G and H are equivalent? We want to show that G plus J equals H plus J for any J. That's what we want to show. And to show this, let's try to break this up a little bit by saying, this is the sort of tricks that you do in your abstract algebra courses, I think. So if you've done those, then this will be kind of oddly familiar, like adding 0, but 0 is written as A minus A. That's the sort of trick that we're going to do here. So we start off with G plus J, but we are going to write it as now G plus J plus H plus H. And why can we do this? We can do this because we know H plus H to be P, and we know that adding P to any game does not change its outcome. But now we do some grouping, because remember, our goal is to get to H plus J eventually. So let's try to write that down as G plus H plus H plus J. Notice that H plus J is what we want, and G plus H is something that we know to be P by assumption, because this is the direction that we are trying to prove right now. So assuming that G plus H is P, we want to show that G and H are equivalent. So G plus H is P by assumption. And remember, if you smash a P onto anything, it doesn't change. So this is indeed H plus J. But that's what we wanted to show, right? So we started off with G plus J, and we have arrived at H plus J. So those indeed have the same outcomes, no matter what J you pick. So this is agnostic to the choice of J. We achieve this just by adding H plus H. Okay. So that's the claim I wanted to show ahead of our main sort of idea. Our main result here is that any game is equivalent, or by which I just mean it sits in the same equivalence class as a game of the form star n, which is a single nim heap with n sticks on it, right? And in fact, we are going to show this in some sense procedurally or algorithmically. I'm going to give you a way of labeling the states of any game to you, like with one of these star n's in a way that these labelings preserve the equivalence that is being claimed, right? So the overall framework is in some sense going to be by induction. So what we are going to say is label all the P states of your game tree 0. We do know that among all of these single heap nim games, so there are as many of them as there are natural numbers. What we know about the single heap nim games is that all of them are n's except for the one that's empty, right? So if you have just a single heap, then the first player just empties it out. So as long as, so this is a n if and only if n is greater than 0, right? And if n is equal to 0, then it's a p. That's the situation we have with the atomic NIM games. So if you want to say that a game is equivalent to a game of this form and your game happens to be P, then you really don't have much of a choice. This is the only valid label for it, is to label it *0. So you start from there. And now I give you a recursive way of labeling the remaining states. So let's say that you are at some state S of your game tree. And let's say that the state here has some children, which I'm going to assume have been inductively labeled. And this should be intuitive because, well, suppose you have a child that is not yet labeled, then I will go further down that game tree and focus my attention on that child. And let's say that this fellow does not also have all children labeled. There is at least one unlabeled child. Then I will move further down there. At some point, I must get stuck. At some point, I must be faced with a node that only has labeled children, right? So this would be a node where, to begin with, all of the children are P because that's all that we have done at the beginning, right? And well, normally you would just say, okay, all of your children are P. So of course you're going to be an N. In fact, even one P would have been enough for me to come to this conclusion. So label it N and move your way upwards in the tree. So we've done this kind of recursive circus before, but previously we were doing it only to identify outcome classes as being N or P. Now we are going to do this slightly more fine-grained labeling where we want to actually associate a number with each game state. So I'm going to assume inductively that all my kids here have a label. And let's say those labels happen to be N1, N2, and so on, up to some NK, right? And the other thing I can assume inductively, or my induction hypothesis is going to be that these labelings are accurate on their own right, which is to say that if this is some state T of the game, then it is indeed equivalent to the single NIM heap game with N2 sticks on it. Okay, so I'm going to assume inductively that we not only have a labeling, but that labeling is meaningful. It has the meaning that we want from it. So now the question is, how do we label the current node? And here is a proposal. Well, first of all, I know that I cannot label it as any of the existing NIs because we know that the NIs are not equivalent to each other. And I know that if you're a game G and a game H is a child game in the game G, then in this case, okay, so suppose I tried to label this with one of the NIs. Well, would this be a reasonable thing to do? Because well, I mean, at the very least, it's going to depend on the nature of these NIs. So I want to basically say, can we even look at the outcome classes? So for instance, if at least one of these NIs is a 0, then I know that this person here must also, well, you have a P child, so you are an N, so you cannot be a 0. And on the other hand, if everything is non-zero, then all your children are N, so you must yourself be P, so you cannot be one of the NIs. So in particular, if all the NIs are bigger than 0, then it makes sense that we should label this 0. I think that's intuitive. If all the labels happen to be 0, then the outcome, the label that I want to associate, let me just use capital L temporarily to talk about that. This certainly should be 0, because all your children are N states. And so you are a P state. So in fact, this is labeling that we would have in principle already done. But on the other hand, if all the NIs are not strictly bigger than 0, so you do have a 0 child, right? So you have a P child. So now you are an N state. And I want to argue that you actually really need a new label here. You cannot be the same as any one of the labels that has already been used on your children. And in particular, I want to actually say that let me use the smallest label that's available to me that's not already used on one of my children. Okay, so in fact, here's a formula that will kind of capture everything, including the 0 non-zero case. So the label for S, I propose, should be the max of the numbers N1 through NK. And if you remember from yesterday, this is the minimum excludant. I wanted to convey some intuition for why we shouldn't be reusing labels from our children. But in the interest of time, I think there's something that I wanted to say that I'm not quite able to say the way I wanted to say it immediately. So let me just, since we're already a little bit over time, let me just try to quickly convey the main idea for why the max labeling makes sense. And we will stop with that. And I will probably do this a little bit quickly. So if that's unfair, then we can go over it again as well. Okay. So what do I want to show? That this is a fair labeling, which means that whatever this max is, let's say that this max value turns out to be M. What do I want to show? I want to show that this game here, instead of S, let me call it G, because that makes it sound more like a game. So I want to say that G is equivalent to M. So that would mean that I have a valid label. M is the max, right? It's the smallest number that does not belong to this set of labels that have been used on my children. And to show that G is equivalent to the single NIM heap of size M, it's enough to show that the sum of these two games is a P. This is all I need to show, right? And that just means that I have to show you that in the combined game, the other player has a winning strategy, right? And let's just look at what the current player can do. What the current player can do is, for example, play in G and move to one of the NIs, right? And let's say that you move, okay, so actually maybe it's a little bit easier to talk about M. So suppose the current player plays it in M and transforms it to some MI, right? So remember, this is a single NIM heap with M sticks. So all you can do is transform it to some M prime, a NIM heap with some M prime sticks, where M prime is strictly less than M. But notice that any number that is strictly less than M must be available as a label for one of the children of G, because this was the smallest number that was excluded. So anything smaller than it must have been included. So if this is the first player's move, then the second player's response will be to take G and to take it to one of its children that happens to have a label also of M prime, right? So at this point, after two moves, the current player and the opponent player have made their moves. The opponent player has given back to the current player a game which is a P plus P, right? Sorry, a game which is basically a M prime plus M prime. So that's two copies of the same game. And now the other player has the upper hand because they can play to win by mimicking, right? So if that's the first player's move, then we're immediately done. Let me just create a little bit of breathing space. What we want to show is that is P. We want to show that this combined game is P. And what we said is that if the first player makes their move here, then the other player knows what to do. They go to G and they'll be happy there. On the other hand, if the first player makes a move in G, and they make a move to one of the NIs, which is less than M, right? Then, of course, again, the second player can take M to that NI as well, right? So then by exactly the same argument, we are done, right? On the other hand, the first player could also take this game to some NI, which is bigger than M, right? But then inductively, we know that the label NI was the minimum excludant of its children, which means that because it's bigger than M, all the smaller values are available when you go to NI. So you go to that child, which is M, again, must be available because NI is inductively, because this is how we are defining our labeling. NI is the label given to be the minimum excludant of the children of whatever that game had. So in particular, whenever you have a label T, notice that 0 up to T minus 1 are definitely available as children. There may be things that are bigger than T that are also available. That's not guaranteed, but everything from 0 to T minus 1 is definitely available because T is the max. So when you go to a child whose label is bigger than M, then you have a grandchild whose label is exactly M. So that's where the other player is going to take the game. And again, you're left with M plus M, which is again a P. So essentially the other player has again successfully managed to take the game to something that's from where they have a winning strategy by induction. And in fact, in all of these cases, it's also by mimicking. It's clear that the other player was able to transform the game into one where they were able to win just by mimicking. So I just recap the three scenarios. So from here, if you go to NI, which is less than M, then the response will be to take this to NI. And if you the first player plays here and takes it to some M prime less than M, then the response here would be to go to M prime as well. And that's where you're using really the fact that you have a minimum excludant. And let me just color code the responses of the second player. And in fact, we are close to, well, a few minutes to 1. So this would be a good place to stop. I wouldn't have gone over time, except that this seemed like a logical place to conclude. So I was very tempted to finish this piece of argument here. And this is really one of the fundamental things about impartial games, that every game can be associated with a single NIM heap according to this equivalence relation. And I think that's pretty cool and surprising. We are going to actually find a way of adding up these labels, saying something to do with the binary representation of those labels. I think I teased this yesterday as well. We're definitely out of time to get to that today, so we will look at it when we meet tomorrow, hopefully along with some other things. But for now, I'll stop rambling here. And if you have any questions or comments, this would be a good time to either unmute yourself or put them in the chat, whatever is